In this video, we're going to discuss the kinetic theory of gases and the gas laws. Put a long story short, thanks to gases, we kind of understand chemistry in the molecular world. Until we had a good handle on what gases were, it was really hard to explain the universe. But to do that, we had to understand what a gas was, and as odd as it may seem in the modern world, this was difficult. I mean, if you think about the gas, if you look anywhere around you, you can't see it. You can't taste it. You can't touch it. You can't kind of hold it in your hands. It doesn't really look like it's there. Yeah, we can feel the wind, or you can blow on your hand, and we know that we're moving the gas around, but for a good part of history, we just kind of assumed there wasn't anything. If you look to the language, especially Western media and the like, take your breath away. That's kind of was a literal statement. People used to think your breath was part of you. That if you breathed and blew and reached out and had a puff of air hit somebody, that was actually touching them, like reaching out with your hand. When things would go through the trees, and the wind would roll through and make them sway, a lot of the old terms were things like spirits or fairies. Like the wind was a thing. It wasn't air moving. Understanding what gas is took a while. And it was the following couple of relations that helped us come to understand the modern kinetic theory of gas. The kinetic theory of gas basically says gas is a bunch of small particles that largely just bounce around. They'll hit stuff, they'll bounce into each other, they just kind of bounce all over. If you have a container for them, then they will bounce into the walls, hit the other walls, bounce into each other. They just keep moving around. That principle, that they're just a bunch of independent parts moving around, leads to all the observations that we're going to discuss. One way to think about this is treat it like a pool table. Think about it like a pool table. You have a bunch of billiard balls on the end. You have one, and if it strikes and hits, it breaks the other ones free. They go knocking about. They bounce off. Some of them will go down the holes. Some of them will jump out the table. Some won't move very far. But that is, they start moving about. Each individual ball is kind of free rolling. It can hit the sides. It can bounce into each other and deflect off. They're just rolling about the table. This is the general idea of kinetic theory of gas. Individual particles that can just bounce around and hit things to bounce off into other directions. Well, when you do this into a large container, something like, let's say, a piston. If I got a bunch of gas in here, that gas is hitting all the sides, bouncing into the walls. Well, it's pushing on the walls. Remember, pressure is equal to the force over the area. My gas is pressing on those walls. Well, if I shrink my piston down, if I shove it down, all that gas, let me say 1, 2, 3, 4, 5, 6, 7 dots worth, it just has less space now. If you were to find the surface area of our original space versus our second space, it's smaller. We have reduced the size of the container. There's just not as much wall anymore. All this wall on the sides, all the stuff behind it and in front of it, being that these are cylinders drawn in 2D, all of that's gone. So the gas simply doesn't have as much area, but it has exactly as much gas hitting the walls, assuming your temperature stayed the same and none leaked out. Your gas, same amount of gas, hitting a smaller area, result is your pressure goes up. Same force, but tinier area is bigger pressure. Easier way to write that is that if your volume goes down, your pressure will go up. But one of the things we found very early on, and you've seen it if you ever hook a bike tire pump up slightly wrong and you try to press down, And it doesn't actually go into the tire. You didn't quite press it. It just seems to bounce the handle back up. You try to push down, you reduce the volume, and it increases the pressure and shoves your handle back up. Or if it's actually hooked up to your bike tire, it just pushes the air into the tire. As your volume goes down, your pressure goes up. Similarly, if your volume gets larger, your pressure will go down. So for a closed system where you don't lose any gas and your temperature isn't changing, these two are inversely related to each other. Well, you can definitely have situations where temperature is a factor. Let's think about a balloon. And it's got a little bit of gas in there. Well, if you ever take a balloon, let's say you blow it up just a little bit, and then you put it on top of a pot of boiling water. Don't know if you've ever done this. Definitely make sure it's a big pot that it won't seal up. But as it heats up, your balloon gets bigger. Well, there's the same amount of stuff in it. But what happened is, as my temperature rose, my volume goes up. What's happening? Well, temperature is a measure of the average kinetic energy. The hotter you are, the faster your things are moving. And so early on, these were moving kind of slow, and in a second, it might make it that far. But later, they're moving faster. In a second, they might bounce against the walls more often. What happens is that as your temperature increases, you're hitting the walls harder. Your force actually goes up. And so originally, before the volume changed, as your temperature got bigger, you actually had an increase in pressure. Your force became much larger for the same area. But we were in a balloon. Balloons expand. Your balloon had some outward force from your inside gas pushing on it, but it also has the outside air pushing it back. Your balloon, much like a manometer's mercury level, it goes to a certain point and stops. When my pressure inside equals my pressure outside, my balloon doesn't change its size anymore. When we first heat up the gas, the particles move faster. My force is greater. I get bigger arrows on the inside. It expands, but the more it expands, the further my particles have to travel to hit the wall. And so for the same speed, if you have farther to go, you're just going to reach it less often. Eventually, as the balloon gets bigger and bigger, my particles only hit the walls just as often, even though they're traveling farther. The net result is the bigger you get, the more this pressure starts to decrease, which we saw up above. As my volume starts to get bigger, my pressure inside will go down. Eventually, my balloon will expand until the inside pressure matches the outside pressure again. So this is what's happening with a balloon. As our temperature increases, our volume will increase. They work together. But the explanation really just comes down to thinking about those particles. Yeah, they're moving faster because they're hotter, so they push on the walls harder. They make the walls expand. But the further apart the walls are, the less often they'll hit. So as it expands, the pressure pushing out decreases until it matches the outside. Well, my pressure and my volume were related. My volume and my temp. Let's think about pressure and temp. What if I don't have a balloon? What if I have a container? And my walls can't expand? Think like a spray can, compressed air. There's a reason they very strongly warn you never to throw them into fire or store near something hot. Compressed air cans, hairspray cans, spray oils, anything like that, they are very dangerous. Because, originally, these are hitting the walls with so much force, and so we have some force over our area. But as our temperature goes up, well, we're moving faster. We're hitting the walls more often. My force gets bigger for the same area. Because my can can't expand like a balloon can, the volume doesn't change. So what's really happening here is that my pressure gets bigger. And so as my temperature goes up, presuming that my volume can't change, my pressure goes up. They are also related directly to each other. This actually raises the question is we have to know what situation we're in. Generally, only two are allowed to change. From our pressure, our volume, and our temperature. As long as you can keep one of them the same, the other two's relation goes hand in hand. When you compress a gas on the bike tire pump, it actually does heat up your bike tire pump a little. If you ever pumped up a really big tube of some kind, you might have noticed the bike tire was physically hot at the end. Initially, when you compress, you increase the temperature. But since that air moves into the intertube and expands the intertube, in theory, what you really changed was the volume. But it takes a little while to play out. It has to balance those forces. It takes a little bit of while for it all to shift around. If you wait long enough, well, temperature will just equal whatever room temp is if you give it a moment to cool off. And so generally, if you're pumping up a bike tire or an inner tube, we don't think about the temperature changing. It's just pressure and volume, but you have to give it a moment to reach equilibrium, to let everything kind of balance out. In those situations, we can figure out what the volume will be, or what the pressure would be, by assuming temp will be the same at the start and the end, as long as we gave it time to do so. Similarly with the balloon up above. We said what's really making it expand is that temporarily the pressure goes up. By giving the balloon time to expand, we allow the pressure to go back to just matching the outside. But for a brief moment when you first breathe into a balloon, we can't really see it with the human eye, but for 30 microseconds or something, it's resisting expansion. The pressure inside is greater until the elastic polymer finally gives a little bit and it stretches and expands, in which case your volume goes up, your pressure goes back down until it reaches where it's supposed to be matching outside. So there's a little bit of back and forth. You have to give it time. If you give it time, though, generally we can assume only two of these are really different, which makes these relations work really well. But we did mention breathing into a balloon, which brings us to our next one, moles of gas. So while there's PV and T, there's also N. So moles in gas law are N, number of moles, is all it really represents. But if I have a balloon and it's got a little bit of gas in it, and I just breathe into it again, the balloon gets bigger, because now there's more stuff in it. What's really happening is the more stuff, as soon as it gets in, starts hitting the walls more, pushes the walls out further. Well, more particles hitting the walls means more force, so your pressure goes up really quickly, expands the balloon, which causes the pressure to go down until it matches the outside. As our moles of gas increase, the volume will increase, assuming we're allowing our volume to change. If I have a container that's sealed, and I suddenly put a whole bunch more moles into it, well, if I can't change my volume, I just have more things hitting the walls more often. Instead of 3 things bouncing, I now have 6 things bouncing. The net result is I just have more impacts per second. More moles will equal more pressure, assuming my volume isn't allowed to adjust. So we have relations between pressure, volume, temperature, and the amount of gas, the moles. Each of these relations can help us determine changes in forces, but really, instead of looking at them individually, what happens if you do have a situation where all of them change? What if you blow up a balloon in a refrigerated room that's overpressured and then you step outside where it's a hotter day with a different pressure? You're going to have a different temp, you're going to have a different pressure, and your volume's going to alter. If we want to relate all of them, we need the ideal gas law. And the ideal gas law lets us relate pressure and volume to moles, R, which is a constant we will discuss, and temperature. Instead of saying, hey, an increase in pressure is going to result from a decrease in volume, we can actually just relate all four to each other at once. Whatever my change in pressure, whatever my change in volume, whatever my change in temp, I can find the new moles. Or whatever change in moles, whatever change in temperature, whatever change in pressure, I can find the new volume. This allows us to calculate out the state of all of these at once. So the ideal gas law is very handy for real-world situations where it's very hard to ensure one of your variables doesn't change, or to make sure only two variables change. What is R, since we introduced here? R is a constant. Since we're working with so many units, if we rearrange pressure and volume over NT to equal just R, depending on what our pressure units are, or volume units or anything like that, if you took a real balloon, and so here's a real example. If I have a balloon and it has 1 mole of gas inside, and it is 1 atmosphere outside, well, it means my moles on the inside are going to match, or the pressure on the inside is going to match pressure on the outside. If I say the temp is freezing, so 0 degrees Celsius, which is 273 Kelvin. So I have a balloon, it's got 1 mole of gas, the pressure outside is 1 atmosphere, it is presently 0 Celsius. That real balloon will be 22.414 liters in size. That is just the size it will actually be if you go and measure it. Luckily, these gas laws, they're consistent for all gases. It doesn't matter what gas you use, it's based on the number of particles. All it is, it comes from the kinetic theory, it comes from the impacts. And so this will always be the size of 1 mole of gas at 1 atmosphere and 0 Celsius. Well, if we plug all those in, 1 atm, 22.414 liters, 1 mole, and 273 Kelvin. I always do gas laws in Kelvin. Calculate that out, 0.08206 is the value we're going to calculate out. But that's in the units of atmospheres, liters, mole, and Kelvin. If you had done this in millimeters of mercury, it would have been 760. Remember, that's the amount for 1 atmosphere. 760 millimeters of mercury, same volume, same moles, same temperature. The result is I would just get a bigger value. I'd get 62.36 for my value. What is R? R is just what tells us the relation to the size of the units. In the same way, if you wanted to convert a foot to inches, you need to know there's 12 inches in a foot. If I want to relate atmospheres and liters and moles, I need to know what the balancing ratio of them is. And that is dependent on which units I use. That is all R value is. It's there to adjust to make all these related to each other based on which units we're using. So here's 2 of the R values for millimeters of mercury and atmospheres. The millimeter of mercury one is also true for torr, since they are the same. It is 62.36 for torr, liters, moles, and Kelvin. So we've introduced a couple relations between materials just to help us explain what is actually going on in gas laws. How those particles bounce, how they impact the walls, how changes in either the pressure or the volume or the temperature or the number will then play out in regards to its impact on the walls, the force with which it hits the walls, how often it hits the walls. All of those components relate these 4 variables to each other in regards to gases.